I'm going to go ahead and start class now. It is 11:32, and I am recording this. So please have your mics muted right now so that I can begin. And then once I need you to turn on your mics, I'll ask you to. But for now, if you can hear me, just go ahead and give me a thumbs up. Good. Good. Okay, good. So that's almost everyone. I'm just waiting on a few people. Max, I'm not going to ask you again. Turn off your camera, or I'll turn it off for you. Okay, so we're going to go ahead and get started. Thank you, Max. We're going to go ahead and get started now. I'm going to go ahead and share my screen with you and remind you where we left off last time. So last time we were on the folder for DNA, and I told you the very, very last assignment that we have to do is going to be this discussion board on mutations. Okay, so I'm going to end the class with that. But first, let me pick up where we left off last time. And where we were last time is I was telling you about DNA replication, and I'm going to pull up that slide. So it's under DNA module, and it's under notes. And we are looking at step 1 of DNA replication. And for those of you who haven't been here in a while, the difference between this class and online class and what we're doing in class is now you are expected to look at these notes. I'm not with you every day to give you notes and to make sure you're taking Cornell notes and summarizing. You're expected to do this on your own. So if you haven't looked at any of my notes, you need to. That's why I'm not meeting with you as often, because now I'm expecting you to read these. So I'm not going to in detail talk about DNA replication because you're supposed to read it. I'm just going to go over the main points. So the last time we were looking at 8.3 DNA replication, and I'm just going to pick up where I left off, and then I'm going to turn it over to you guys in discussion groups so that you can do the mutations 8.7 discussion board assignment. Okay, any questions about anything? Okay, so we're going to go ahead and pick up where we left off. We were looking at pulling it up here. Okay, here we are. So we were looking at step 1 last time of DNA replication, and I'll just pull up like the summary of everything. So this is a very complicated picture of what DNA replication is, but we were only going one step at a time. And I think it was Melissa last time who read us step 1. So I'm going to ask, how about Oscar? Can you read us, please? What is step 2 called? And I'm going to give you a brief summary of step 2. Go ahead, Oscar.
Step 2, framing and elongation.
Elongation. Yeah, thank you, Oscar. So do you guys know what it means to prime something, first of all? To prime?
To get it at the best it can be.
Sort of, Max, sort of.
Prime to like get it going.
Yeah, exactly. Yeah,
fast
Oscar.
and free shipping.
To get it started, to get it going. Think of it like, you know, have you guys ever painted anything? Or have you heard of primer?
Priming, it's also a word used like in like cars.
Exactly.
Like when they're priming the car, like they're priming the gas, so like it's easier to turn on and on.
Exactly, Oscar. And so like when they're painting a car, or if you're painting your bedroom or whatever, right? The primer is it's like the first coat that you put on the bottom to get it going, like you guys said. Okay, so we're going to look at what priming is. Okay, and in my notes, can you read us, please? How about Alexa? Step 2, part A, is called the primer. Can you read us this, Alexa?
RNA primers. Before new DNA strands can form, there must be small pre-existing primers, RNA, present to start the addition of complementary bases.
Right, and I'm going to refresh your memories of step 1, right? We said step 1, the DNA splits, right? The DNA splits, and it makes this little split we call the fork, okay? And like we had said, once you split it, now you have like a zipper that's been undone. You have a set of bases here and a set of bases here, and we're going to use those to make more DNA. And does anyone remember why we said we want to do this? Like, why do we need to make more DNA again? Does anyone remember?
To repair.
To repair stuff, right? So the reason we're doing this DNA replication, we're opening it up, we're making the fork, and then like Oscar said, we're going to prime it or get it ready. And like Alexa just told us, in order to get it ready, we need this thing called the RNA primer. And the RNA primer is basically, it's labeled right here. It's just this little small chunk. It's this little small chunk that kind of gets the whole complementary base thing going. Okay, that's what a primer is. Part B, can you read us please? How about Jessica? Part B.
DNA polymerase.
Polymerase.
With the RNA primer in place, DNA polymerase enzyme causes the synthesis of a new DNA strand in the 5' to 3' direction.
Right, and all that means, Jessica and everyone else, is we start with the DNA primer, okay? The RNA primer, again, is just what gets the whole thing started, but the DNA polymerase, which is an enzyme, is what makes the whole DNA grow. So we add one piece, then we add another piece, then we add another piece, et cetera, et cetera, et cetera, et cetera. Okay, that's all that's happening here. This enzyme called DNA polymerase is basically doing all the work. It's adding base by base by base. Okay, and can you read me, please? I know. Let me refresh your memory. Jessica just told us in the 5 to 3, and you guys remember how we number our carbons, right? Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And what did we say 5 was always? What did we say 5 was? What's the difference between the 5 and the 3? Does anyone remember?
The 5 is the beginning and the 3 is the end.
Exactly. So the 5 just tells us this is where it starts, or the top, or the beginning, whatever you want to call it. And the 3 just signifies that this is the end of it. So as we're making this DNA strand, like you can see right here, if we're using this top one as like the template, does anyone remember what I said template was? Template?
A format?
It's like a format, right, Vanessa? So if I'm using this top piece of DNA, and imagine this being a half of a piece of DNA that we're using as a format, like Vanessa said, and I want to make more DNA from just this template. Well, I'm going to make it in the 5 to 3 direction, meaning, like Jessica just told us, the 5 is the start and the 3 is the end, meaning that we're going to start making it here, and here you can see the RNA primer, meaning this was the first piece we added. We added this little RNA primer, which is symbolized by these blue colors. They're just a set of bases that tell DNA, start making DNA right here. So once this is in place, then we add this one, then we add the next, the next, the next, et cetera, et cetera. But like Jessica just told us, we do it in the 5 to 3, right? Here's the 5 end, and we're going, are we making this DNA on the bottom? Are we making it from left to right, or are we making it from right to left? The bottom one. Are we making it in the left direction or in the right direction? Guys?
The right direction?
Here, let me simplify, okay? I'm gonna sketch you something right now. I'm going to sketch you something, okay? So if I am making a DNA, okay, here's my DNA. These are my bases. Okay, and I'm going to call this the 5, and I'm going to call this the 3, right? Just like you did on your model. So if this is a 5, Maria, what does this side have to be?
The 3.
The 3, right? And if this is a 3 here, then what does this have to be, Daisy?
5.
A 5, right? Okay, very good. So what we're doing here, though, is we're not just going to look at a DNA. You did that for your DNA model. We want to know how do we make more DNA? So what we're going to do, and I think it was Melissa that read us last time, we need to, oops, hold on. I don't want my eraser, I want to write. Okay, what we want to do is we want our DNA now to unzip, right? So we're going to unzip it now. And then we now have exposed these little, and this is step one. This is exactly what we looked at last time. And like Oscar and Jessica told us, we're getting ready for what we call the priming, okay? So now that we have these ends available, and I'm gonna just put some letters just to kind of make this a little more real. If this is an A, this is a C, this is an A, this is a G, this is a G, this is a C, and this is an A. So according to base pair rules, Denise, according to base pair rules, if I unzip this like I did in step one, for step two, which is what we're on now, if I wanted to make more bases, we need to do something first. We need to include what Alexa told us called the primer. And the primer, all it is just a special set of letters that say start right here. So according to base pair rules though, Denise, if I want to make another DNA from what I just drew you up here, what would match up with this letter, Denise?
T.
A T, right? What would match up with this right here, please, Alexa? With this?
G.
A G, right? What would match up with this right here, please, Max? Max. Now he doesn't want to talk. Felipe, what would match up with this?
My bad. It was C. It's C.
It's a C, right? Very
C.
good. What would match up with this, please, Felipe?
C.
Is that G? C?
It would be a C. And what would match up with this, please? How about Christian? What would match up with this?
T.
A T, right? So you guys get it, right? But the point of the primer, like Alexa just told us, is we need to have this first little piece going. And I'm going to label this the RNA. Sorry for my writing. The RNA primer. The primer is basically just like Oscar told us, the thing that gets it started. Meaning it's the first part of this. Okay, is what we call the primer. Now, we're still using a DNA with 5s and 3s. So I'm going to just relabel my thing. So if this was a 5, Maria told us this was a 3, and then Daisy told us this was a 5. Okay, but check it out. And let me erase my writing here. But check it out. If this is a 3, now we're making a new DNA. So Dominic, for this new DNA that we're starting to make right here, if this is a 3, then what's this? Dominic, on the new DNA. So I'm going to
sorry.
So I'm going to call this we're going to call this the template. So this here, we're going to label template. Oh my gosh, sorry for my writing. This is the template. And then here, this is the new DNA. Okay, so here's my new DNA. And then, so Dominic, we're making a new one here. And so on the old template, the end here was a 3. So what's this new one again?
On the other side?
The one I'm pointing to right here. I'm making a new DNA from this old template. So this end right here.
Oh, 5?
It'd be a 5, right? So this is a 5. And so what would this have to be over here, please?
3.
It'd be a 3, right? Very good. So you see, all I did is I unzipped my DNA, step 1, and now step 2, I'm using this template to make a new DNA from it, but we're still following the 5-3 rule. Like Jessica told us, 5 is the start, 3 is the end. So in which direction then is this DNA being made, Victor? Is it being made from left to right, or is it being made from right to left?
Can you repeat the question?
Yes. Is this DNA the new one? The new one I just labeled at the bottom. Jessica told us that DNA gets made in the 5-3 direction when we're making new DNA. So this new red DNA that I labeled at the bottom, is it being read from left to right, or is it being made from right to left?
Right to left,
Do you agree, Denise?
left to right. No, right to left. Yep. Final
Okay.
answer.
Okay, Victor's final answer, right to left. What do you think, Melissa? In which direction is it being made? Right to left or left to right?
Right to left.
Okay, what do you think, Noemi? Right to left or left to right?
Right to left.
Very good.
So I was right.
You were correct. It is being made in this direction because that's the rule. Jessica told us it gets made 5-3. But think about this. If this one's being made this way, if we were to make a brand new one over here, and let me expand my model a little bit so that I have more writing. Okay, let me make this a little bit bigger so we have, oh, let me change my color too. Don't forget I'm recording this so you can always rewatch this. Oh my gosh, what am I doing here? Okay, so I'm gonna make my model a little wider. So I'm gonna make now another new DNA, just like I did at the top. Can one of you on the bottom remember how you guys can write on my screen? You have the you have some options on your screen, and I'm going to ask whoever feels confident enough to draw me the other DNA strand that would be made here using the same exact rules that I just did. And I'll make it worth your while. Whoever can make me the other side of this DNA strand and put your name on it, I will give you extra points. Whoever can make me the other DNA, please. So this is Denise writing for me. Very good. But Denise, hold up, Denise. You're on the wrong side because this is the template. The new DNA needs to be made in here. You're making it outside. So who can make the correct DNA model, the other DNA side? Okay, so Denise is drawing. Very good. And then remember, I already gave you the formula up here, DNA. I already gave you the DNA right here, Denise. So match the rest of it. So it read A, C, A, G, G, C, A. So what's missing? Here. Okay, that looks like a T, right? So what's this? What's this over here? Okay, G, very good. What's this? Okay, that looks like a T, okay. I think you guys need to write a little bit smaller because you're gonna run out of room, but you're on the right track. Okay, that's a C, very good. That matches to that G, very good. So what's this gonna be then? Very good, C. What's this? Good, G, and lastly, T. And I think I put too many, huh? So don't count these last ones. Okay, oh my gosh, what did I do? Hold up. I just wanted to erase. Never mind. Okay, so very good. You got the DNA template side done, but what about the other side? You only drew, Denise, you only drew the template actually. You didn't draw the new DNA one. The letters that you wrote, Denise, are only the match for my template that I unzipped, but you didn't draw me the new DNA. Does that make sense? Hold on, what are you writing there, Denise? hold on. Let me erase because this is getting the letters are too big and it's actually taking up a little bit too much space. But you got the formula right, Denise. Let me just show you with smaller letters what the match would be, okay? Because that took a little bit too much room. So let me just draw what you wrote. So you said it was T, you said it was G, and I'm just doing Denise's but smaller, okay? So T, C, C, G, and T. Okay, so that's the template, right? These are templates. But that wasn't my question. My question was, what would the new DNA? I'm going to do it in another color just so you can see, right? We're making a new DNA here. So according to the base pairing rule, what would match up to this T, please? How about Oscar? What would match up to this T? I'm making another new one, right? I'm making another new DNA. Right, new DNA. Okay, very good, Oscar. Hold on, let me just finish writing. Okay, so you said it'd be an A over here. Very good. What would match up here?
A C.
Very good. What would match up to this C?
G.
Very good. What would match up to this C? Very good, a G. And what would match up to this T? An A. And what would match up to this G?
C.
C. And then what would match up to that T?
A.
An A, right? Very good. Okay, so check it out. We had said, and actually Victor told us correctly, that this DNA would be made from right to left. But check out this new one that we just made. Watch this. So if this is a 3, Daisy, you had told us at the beginning, what is this end then, right here, Daisy?
5.
That's a 5, right? But check it out. We just made another new one. So if this is a 5, what's this, Daisy?
3.
A 3. And what's this up here, please, Dominic, for this little red one we're making?
A 5.
A 5, right? So now, Dominic, in which direction is this DNA being made? Is it being made from left to right or right to left? According
Left to
to
right.
just, very good. It's being made in the opposite direction. It's being made this way, okay? Now check it out. You've made 2 DNAs here, guys, using the rules, but these 2 DNAs are actually different and they have 2 different names. The way we can tell the difference between the 2 DNAs that are made during step 1 and step 2 is it depends on which direction they go. So Victor told us that this DNA is being made from right to left, and Dominic just told us this new one is being made from right to left. I'm sorry, left to right. I'm confusing myself. So the way that we differentiate or tell the difference between the 2 is what they're splitting towards. In step 1, remember we had said there was a little split that happens right here, this little unzipping. Does anyone remember what the name of this little split is called? The little split, what do we call that split?
Fork cut.
Close.
Fork.
Close.
Fork split.
It's called, yeah, you're close. This little split here, we call it the replication fork. Remember that? Okay, the split is called the replication fork. And the way we tell the difference between, okay, which DNA is this and which DNA is that, is it depends which one is going to the fork versus which one is leaving the fork. The one that's being made in the direction of the fork, meaning it's going that way, it's going towards the center. This one has a special name, guys. The name of the one that goes to the fork, I'm going to put it in parentheses. Okay, this new DNA right here, this new DNA right here, the one that goes to the fork, we call it the leading strand. Please, if you're not writing this down, you can always rewatch this video. But the one that happened, and again, this is all covered in my notes, I'm just reviewing the notes. The one that gets made in the direction of the fork, meaning it goes to the middle of the fork is called the leading strand. The one that goes away from the split, the one that is being made, like Dominic told us, from left to right, the one that goes out, what's that one called?
The lagging strand?
Very good. It is called the lagging. And again, this is all from my notes, so if you haven't read it, you need to. This is called the lagging. And think of it like this. The one that goes to the fork, just think of it, it's leading you to the fork. The one that goes away from the fork, it's a little bit slower and it goes backwards technically, so we call it the lagging strand, okay? The lagging strand. And sorry for my writing. All right, and that's it. That's step 2. Step 2 just tells us we start making our DNA, but we make 2 of them. We make them in the 5 to 3 direction, always. The one that goes to the fork, we call the leading. The one that goes away from the fork, we call the lagging, okay? So I'm going to minimize this drawing. I'm not going to delete the drawing. I'm just going to minimize it. And I'm going to go back to my notes. And like Jessica told us, the boss, the one that does all the work, the one that glues letter by letter by letter, like you see here, that's called DNA polymerase. It's what causes, like Jessica told us, all of the DNA to be made in the 5 to 3. But remember, the 5 to 3 can happen in 2 different ways, right? It can happen this way and it can happen that way. Does that make sense, guys? Give me thumbs up if you understood what I just said, or if you understood my drawing. Give me thumbs up if you understood what I just said. Thank you, Denise. Thank you, Maria. Thank you, Vivian. Thank you, Vanessa. Thank you, Melissa. Okay, good. So again, I'm recording this so you can always revisit, but I'm just explaining my notes a little more in detail because I know they're kind of complicated, right? But that's step 2. We use DNA polymerase to do all the gluing letter by letter. We revisited what 5-3 meant, and Victor and Dominic helped us figure out in which direction our DNAs go. And remember, they're anti-parallel. What did we say anti-parallel means again, guys?
They touch the whole time.
Not quite. Thank you, Max. What did we say anti-parallel means, guys? It's one of the DNA rules that you did in your model.
Going in different directions?
Thank you, Vanessa. They go in different directions, right? And on your model too, Vanessa, you labeled top and bottom, and top and bottom are just labeled with 5 and 3, okay? So we just said the leading one is the one that goes to the what, Oscar? The leading one goes to the what?
Replication fork.
Towards the fork. Very good. And the lagging, Melissa, what did we say the lagging was? Melissa?
Yeah.
What did we say the lagging was?
Like the slower, I don't know.
It's on the board. You guys see my board, right?
Yeah.
You see what I'm highlighting?
No.
You guys can't see my screen right now? What do you guys see?
I can see it. I can see it.
What does it say on my screen? Do you see what I'm highlighting?
No.
What do you guys see on my screen right now?
We
I see the model.
Huh?
I see the whole model.
You don't see words right now?
I see the whole model.
We can see the DNA splitting into the fork and the words like labeling it with the
You
like
mean
lagging.
The drawing that I
leading
did, you
strand.
mean? The drawing that I did?
Yeah, we can see that.
Oh, okay. I thought, okay, sorry. I thought you were looking at something else. Here, I guess I'm sharing the wrong screen with you. What I meant to share with you is, can you see this now?
Yeah.
Okay, good. Sorry about that. Okay, so like I was asking Melissa, so what did we say the lagging strand does?
It synthesizes in the 5-3 direction, but
discontinuously away from the replication fork.
And discontinuously means, like you just said, like slower, not all at once, right? It kind of lags. That's why we call it lagging. But the key word there, Melissa, is it goes away from the fork. And because it goes away and because it's discontinuous just means like in chunks or in pieces. The names of those little chunks, we call those things the Okazaki fragments. You don't have to worry about Okazakis. I'm not going to ask you this on the quiz, but because it's not even in the book. But the Okazakis are the small little segments of strand, because the lagging is not all, all at once. It goes in small little fragments, and the ligase is the glue that technically binds them all together. So I'm not going to ask you to worry about this. I'm just going to ask you about leading and lagging. Okay, and here's a picture of the whole thing. And that's step 2. That's all of it. Okay. Step 3 is very easy. Step 3 is just the last part. Can you read this, please, Jessica? What is step 3? And I'm going to end right here with this.
Step 3, proofreading and termination.
Jessica, who's your English teacher?
Miss Nelson.
Does Miss Nelson have you proofread?
Yeah.
Well,
You guys proofread
yes.
in her class? What does it mean to proofread?
To check
So like
the
correcting.
To check, right? To check and make sure there's no errors, to correct it, like you said, right? So step 3 is very simple. All we want to do is we want to make sure that the DNA bases are correct. Because remember in that drawing I did where I said A matches to T, and then Oscar told us G goes to C, et cetera, and then Denise was matching it. Did they match them correctly? Did they match them correctly when they wrote on my screen, guys? Did they match them correctly? Or did I match them correctly? Did I match them correctly?
What did you, yeah.
I did, right? Because you saw me do the letters and we created the leading and the lagging, right? The point of step 3 is this, is if they don't match, Felipe, if there's a mistake, we have these enzymes that I highlighted in red called exonuclease and DNA polymerase. Their job is to make sure the correct bases are there, right? Because did we ever match A and A together?
No.
Did we ever match T and G together?
No.
Did we
No,
match C and C together?
No.
no.
No, right? Because we did it correctly. So if there is a mistake, guys, we correct those mistakes with the enzyme exonuclease and DNA polymerase. All you need to know about them is they make sure that the correct letters are there. Make sense? Just the correct letters, meaning A's the T's, G's the C's. Make sense?
Yeah.
Yeah.
Okay, so that's it. That's what DNA replication is. It's much more complicated than it sounds because there's so many big words in there. But please just look at the drawing that I did in the video I just recorded. That pretty much summarizes the whole thing. Step 3 is just the end, right? We make sure everything is correct. And then to terminate something, as in Spanish terminar, to terminate means, okay, let's end, right? Because remember, all we're trying to make, I'll go back to this picture of the bubbles. All we're trying to make is if we're trying to repair a bone, like we said the other day, right? If I want to repair a bone and the instructions to repair that bone are right here, all I want to make is the DNA that goes from here to there, and then I end, right? I'm not making all of my DNA at once. I'm just making those small little sections. So once we reach the small little sections and we correctly paired it, it terminates, meaning done. Similar to how I'm done. Okay, so that concludes DNA replication. Please rewatch that video because I'm sure you're going to have other questions about it. Okay, so what I want to do now, guys, is I'm going to put you in groups. We have 23 minutes left. And what I want to do is I want you guys to open up the Schoology discussion board. And I'm going to share my screen so you know where to find it. You go to Schoology. You go to DNA module, you go to discussion board, and then you're going to click on mutations. Okay, so let's read the assignment first. It's a long one, I know, but don't worry, I'm going to explain it. Can you read us the instructions for this? How about April? Can you read us the instructions for this discussion board? April, are you there? How about Victor? Can you read us the instructions for this discussion board?
Yeah, I can do that. Most genetic disorders, mutations, are associated with an alteration of DNA, either on the chromosome or on the DNA sequence itself. These chromosome genetic disorders can be either numerical or structural changes in the chromosome. Numerical disorders occur when a DNA chromosome is either missing or has an extra copy. For example, Down syndrome is an example in which 3 copies of the 21st chromosome exists instead of 2. Structural disorders occur when a portion of DNA chromosome is missing or replicated or moved to the wrong place.
Okay, so let me pause you there. So all of this was in my notes, section 8.7. When we met on Wednesday, I asked you guys to preview that section of the notes on your own, because you're going to use what you learned since Wednesday right now. So if you didn't get that information, you didn't do your homework, basically, Victor just summarized it for you, pretty much, okay? And it is that there's 2 ways that mistakes happen, and those mistakes are called mutations, right? And in step 3 of DNA replication, we just learned that we don't want bad stuff to happen. We don't want the wrong letters to match up, right? That's bad. So if for some reason the mistakes still happen, we call that a mutation, okay? Unlike X-Men, usually mutations that happen in the DNA, they don't give us magical powers, okay? What mutations do is they can change something in our bodies, and there's 2 ways that happens, right? Victor just told us one way is that it's a change to the chromosome. That's one way, okay? And that can be something like the numbers are different, right? Meaning, like in the Down syndrome, which is something we've already talked about in class, Down syndrome, like Victor just told us, rather than having just 2 copies per chromosome from mom and dad, for some reason they get 3 copies. That would be a numerical type of mutation of the chromosome. The other type, like you just said, Victor, is it can be a structural. And structural meaning the chromosome itself is weird, meaning something could be missing, something could be replicated or duplicated, like there's something wrong with the chromosome itself, okay? That's one way. But the other type of mutations, can you read us, please, Noemi? What are the other types of mutations, Noemi, that I just highlighted?
However, other mutations can simply occur when a segment of a DNA sequence, similar to the ones you use to build your DNA model, is changed, as can be seen in the problems below.
Very good. So like in your models, right, you were all given a sequence, right? You were given a sequence for like being right-handed, right? TTA. You were given a sequence for being left-handed, right? ATA, or whatever the letters were. So the other types of mutations, the ones we're going to talk about right now, like Noemi told us, are when simply, and sorry, this is simple, it should be simply, occur simply when the DNA sequence is messed up. Meaning rather than going ATA, it now gets changed to like ATT or something, right? So what you're going to do right now then, knowing what you know about how mutations work, which I'm going to go back to my notes, and for those of you that didn't do your homework, it's all covered right here, okay? So in your discussion groups, what you're going to do is you're going to use these notes to talk about this discussion board prompt that Noemi just read us. So down here, I'm giving you guys an original DNA, and then I'm giving you what I'm calling a mutated DNA. So can you tell us, Noemi, what are you guys going to do with these sequences now? I just highlighted. Noemi, can you read that?
Using your knowledge of DNA mutations, identify in each of the original DNA sequences what changed in the mutated DNA sequence specifically and predict its effects.
Okay, very good. So like Noemi just told you, you're going to look at the original DNA, which is highlighted right here. Then you're going to compare it to the mutated DNA. Then you're going to list what is the change and what is the mutation. Okay, so use your notes to answer both of these questions. This should take you no longer than like 5 or 10 minutes. Then we'll come back and do a debrief so that you can answer this part, okay? So I'm gonna go ahead and put you into groups. We'll do, let's do 4 groups, okay? So you'll have about 5 people per group, and I'll be jumping around per group. So please have your notes for 8.7 mutations open, and your job is to answer those 2 questions that Noemi just told you, okay? So here we go, guys. Accept my invite, and I'll be jumping around per group. I'll see you in your groups. Donna, you have to accept my invite. Danos, you have to accept my invite. I think you might have stepped away from your computer. If you're not there, accept my invite. Okay. Hi, group.
Hello,
can one of you guys share the screen so that we can work for the discussion board?
You share a screen for the discussion board?
Yeah.
I could try here, but let me just make sure. Because I'm just using my phone right now.
Can someone share their screen, please? We need to look at the notes in case you forgot what the mutation types are. And then we're going to use those notes to, thank you, Noemi. So these are the 2 mutations. Thank you, Noemi. So these are the 2 mutations. So we're looking at the mutated versus the original. Who can tell us, first of all, what changed here in the sequence? Can you enlarge it a little bit, Noemi?
The first one doesn't look like it changed.
Are you on a computer or your phone, Noemi?
I'm on my laptop.
Okay. Can you?
I can just zoom in though. That's fine.
Okay. Yeah, you can zoom in individually on your own screens, but does anyone see what the difference is between the original and the mutated for the first one?
The second.
It's practically the same except the AG. It's AG instead of AC.
Can you hover over it, Noemi, with your little cursor? Can you show us? Okay, very good. So right there, right? So the C changed to a G. Yeah. So that's what changed. But what type of mutation is that? So right now, this is where I need you to use your notes, and I want an answer. So please use your notes. That has a name. That has a name. So I'm going to jump around per group now, and I want you to tell me for both of these, Noemi and Felipe and everyone in this group. I want you guys to tell me for both of these, what are the types of mutations? Okay, so I'm going to leave this group. I'll be back. All right, hi guys. So who's sharing their screen with us? Guys, who's sharing the screen? Who's helping us do the problems? Thank you, Christian. Good. Okay, good. So Christian and group. This is the original. This is the mutated. Can someone tell us what is the change? Like, what is mutated here between the original and the mutated for the first one? What's the difference?
In the first 3 letters, the original says ACG, and then the mutated one says AGG.
Perfect. So that's the change, but that's not the mutation type. So what you guys need, Vivian and company, you need to figure out what specific type of mutation that is. So you need my notes for section 8.7 to tell me the name of the mutation for both problems, okay? So very good. I'll be back, and I want an answer for both, okay? But you're on the right track. So someone, Christian or Vivian, whoever, share your screen for the notes. If you already know the answer, then talk to your group. But if you don't have the answer, share your screen, Christian, for the notes on 8.7, and I want an answer for what types of mutations both of these are. Clear?
Yes.
Okay, good. I'll be
The Sickle-Cell Disease.
Okay. Hi guys. So Denise, you're sharing the screen. Okay. So for the first one, sorry to join you late. What is the change between the original and the mutated here?
The changes are like in the first set of like the DNA.
Mhm.
Like in a mutated replaces it, like the C with like the G instead.
Can you hover over it with? Are you on your phone or your computer?
Phone.
Okay. Can you click on the letter you're saying is different?
That I can't do.
Oh, you can't.
Wait.
Yeah, it may be difficult on a phone. There it is. Yeah, right there. Perfect. Thank you. Right there. Okay. So very good. Denise, did everyone else catch that?
I was the first one to catch that. I think,
Oh,
yeah.
okay. Does everyone else see that though?
Yes.
Vanessa, Daisy, April, Melissa. Okay, good.
Yeah.
So, okay, good. So now that's not the question I'm asking you. That's the change. But now my question is, well, what kind of mutation is that? So what you need to do, Denise, is share your screen for the mutation notes, section 8.7. There is a specific name for that, okay? So I need you to go into your notes and I need you to tell me what happens, like what kind of mutation is that, okay? So please pull up your notes. And
Mr.
for this, yeah, go ahead.
Aren't there like 4 different types of like, I want to say like mutations, like insertion, deletion?
Very good, Melissa. Very good. Yes, you're on the right track. So without giving the answer to your group, Melissa, pull up that section of the notes because it's clear you read them, but I want to make sure we all get it. So how about Melissa, maybe you share your screen. And you're right. There are insertions, there are deletions, there are replications, like you said. But I want to know specifically which one this is. Does that make sense?
Yeah.
Okay. So someone else share your screen, and I'll be back. But I want an answer, okay? I'll be back.
All right.
Hey, guys. So who's sharing the screen for us here?
We already did that. Alexa.
Oh, you already figured out the mutations?
Yeah.
What were they? What were they?
In the first one, it's in the first section, it's ACG, but then on the mutated version, it's AGG.
Okay, and on the second one?
On the second one,
an extra T, I believe, in the mutated version, and then some pieces did not match.
Okay, can you actually, Jaime or someone, can you share the screen though? Because I want to point something out. You guys are right, Dominic and Jaime, but I want to point something out to you. So can one of you share your screen, please?
yeah, I got to get to it.
I'll do it.
All right, you got it.
Thank you, Alexa. Okay, so you're right, Jaime and Dominic, but there's a name for these mutations.
It's substitution, right, for the first one?
Thank you, Alexa. Very good. So can you tell everyone, Alexa, because it's clear you read my notes, what is a substitution mutation?
It's when there's a change in one of the bases or the letters in the sequence.
Mm-hmm. And so what was substituted exactly, Alexa?
Instead of being C, it was substituted to G.
Fantastic. Absolutely right. And for the second one, Jaime, you told us something was different, but what's the name of that mutation? Jaime, don't tell him, Alexa, because I know you read my notes. I want to see if Jaime read my notes. So what happened in the second one then? What kind of mutation is that?
I forgot what the mutation was called.
Okay, so that's okay. That's why I need you guys to pull up the notes and tell me the specific name of that. So Alexa, I think you read my notes, but I don't want you to give answers away. So can you pull up the section for 8.7 and help them find what kind of mutation the second one is? Does that make sense? Okay, so share your notes. 8.7.
I don't know why it's not pulling.
I can see it. It's just kind of laggy.
Yeah.
Okay, so scroll all the way to 8.7.
DNA insertion. All right.
Insertion? Okay, and what kind of mutation? Yeah, so first pull up that section. Yeah, it's kind of laggy for some reason. There you go. I see it now, Alexa. So click on slide. Keep going.
This one?
Keep going.
Which slide is it?
Right there. Freeze right there. So you're right.
Okay.
Jaime, you're right. You said that was an insertion, right? Jaime?
Oh, yeah.
You said insertion, right? So it is an insertion, Jaime, but specifically, we call those frameshift mutations, okay? So when we inserted that letter, Jaime, did you notice that there, it looked like there was that extra set of letters at the end, right? Because what we did was by inserting, like, for example, in this funny little sentence, it reads, this is DNA, okay? Pretend these are the letters of the bases in DNA. If the sentence originally reads, the fat cat ate the rat, but then we insert an extra letter like we did in that problem, Jaime. If we insert that H right here, now read the sentence. Read the sentence to me, Jaime.
The fat cat ate the rat.
You see how that doesn't make sense, right? So when you insert something like that, Jaime and Alexa and Maria and Dominic and Angel, when you insert something like that, you're not substituting anything like the first one. You're actually changing the entire sentence. And have you guys ever heard of like a sentence frame? Have you heard of frames? Like in English class, they say, here's a sentence frame. Have you guys heard that before, that term, frame?
I think so.
Okay, if not, that's okay. Frame just means basically like a sentence, okay? So because we inserted that H, guys, like Jaime told us, when we insert that, you saw how it pushed the entire sentence down, and now it's not legible, right? It doesn't make sense, right, Jaime? That sentence you read, it doesn't make any sense now, right? So when that happens, when we insert letters, or even if we delete them, because look, if you take out this H now, this sentence doesn't make sense either, right? Look, tef, atka, ata, tet, gur, at. It doesn't make sense. So if you insert or delete something, you change the way the DNA is read. And that, my friends, is called a frameshift mutation. Can you go back on a previous slide, Alexa? Yeah. And when you just substitute, like you said, Alexa, that is called a point mutation. You see the difference there?
Yeah.
Okay, perfect. Good job, guys. Excellent, excellent job. So I'm going to go ahead and leave this group because you're my last group. Everyone already talked about this. I just wanted to check in with you guys. But great job. All right, so everyone is coming back. Well, that was awesome, guys. I went to all the groups and everyone was able to very quickly identify what the change was. And I went to all groups. Not all groups were able to get the names of the mutations right away. So some of you had to look at your notes and figure it out. But I think most of you were on the right track. So I brought us all together here just because I wanted to just share out all the different groups and what they came up with. So can we do, the first group that I talked to was Noemi, you were the one sharing. So can you tell us, Noemi, and I'm going to share my screen now, or anyone from Noemi's group. So I'm going back to Schoology. So specifically, Noemi's group, what was the change here?
There was a change between the C and the G.
Okay.
Or is it when it gets...
Okay. So there was just a change between a letter. So what kind of mutation is that, Noemi's group?
What?
What kind of mutation is that?
Noemi's not here. Oh, wait.
It would be point mutation.
It is a point mutation. Very good. So for those of you that didn't look at my notes, I think Melissa told us this earlier. There are insertions, there are deletions, there are all substitutions, like you said, Melissa. However, we categorize them into two. So let me share with you this. There are what we call point mutations, like Noemi said, and a point mutation is where simply one letter swaps out for another, okay? So in this little silly sentence, right, pretend these are the letters of DNA. The fat cat ate the rat, okay? Pretend these are letters, right? So if we substitute, like you did in that same problem, Noemi, if we substitute that letter C for letter H, now the sentence reads, the fat hat ate the rat. Okay, so that substitution that you just talked about is called a point mutation. Now, for the second one, the second group I went to, the person that was sharing, who was in my second group? That was, I think, Christian's group. Christian's group. What changed here, though? What changed? Go ahead.
There's an insertion.
Very good.
Like
where?
At the end, there's an extra T.
There's an extra T. This T or this T?
The very last one.
You're saying this was inserted? Is that correct?
Oh, well, okay. Well, the spacing looked off, so I was confused. Okay, never mind. It's the first one then, huh?
It's the first. Yeah, very good. It's the first one. And the reason the spacing looks off, and I did this on purpose, guys, is because when you insert an extra letter like that, check out what happens. When you insert an extra letter like that, like in my silly little sentence again, if the sentence reads originally, the fat cat ate the rat, but then we insert this extra H, check it out. Now it doesn't even make sense. The fat hooka tat et and then there's an extra T, like you said, right? There's an extra T that throws off the way the structure is. We call that a frameshift mutation. Specifically,
your screen froze.
Oh, my screen froze? What do you guys see? What do you guys see on my screen?
It's just frozen.
Uh-oh. My face is frozen?
We can see like the conditioning phase. So it's like you tried switching pages, but it like paused halfway through.
Oh, hold up. What do you guys see now? Just me, right?
Yeah.
Okay, let me try this again. I'm sorry. I don't know what happened there. What do you guys see now?
The notes.
The notes.
You see frameshift mutation?
Yeah.
Okay, sorry. So Noemi told us the first kind of mutation was a substitution where we substituted a letter, but the name of that is called a point mutation. Okay. The second example, like Vivian told us, is we inserted an extra letter. When we insert or even delete letters, what happens is you change the way it's read, right? Because now the sentence doesn't only not make sense, but now you have this extra weird spacing, like Vivian said. Same can be said if we delete a letter. Look, if we delete a letter, now the spacing is different because now we don't have chunks of 3 letters. Look, now there's an extra 2. So if you insert or delete, we call that mutation a frameshift, okay? So now the assignment. Now the assignment for you is, can you read us, please? How about Maria? Can you read us this last part?
Lastly, once you have answered the 2 problems, create your own original sequence and similarity. Mutate is as shown. Your job is then to solve at least 2 other students' DNA problems. List the type of mutation and occurs and predict its effects.
Okay, so same how I just did here, Maria. You're going to make me your own original DNA. You're going to make a mutation on it, and our job for 2 students, you're going to try to figure out the same exact thing, what type of mutation it is. Does that make sense, guys?
Yeah.
Okay,
yeah, so we just say if it's like a point mutation or a...
Well, no, you're not going to give us the answer. You're just going to write the question. You're going to...
For other people.
And then we're going to try to guess it, right? So if this is Trujillo, if this is me, I'm writing my original, okay? And I'm going to write it, AAA, oh, sorry, AAA, TTT, et cetera, okay? Then I'm going to make my mutated, right? ATA. Does that make sense? And then your job is to reply to someone and say, well, that's a insertion frameshift, or that's a point. Does that make sense? You have to guess each other's. Does that make sense, guys?
Yep. Yes.
Okay, that's it. So this should be a very simple assignment. All you need to do, like Maria said, is just create one. Just create one and respond to 2. Sound easy enough?
Yeah.
All right. All right, guys. So thank you very much. I know we went over 3 minutes, so I'm going to go ahead and end class now. Does anyone have any questions about this DNA stuff?
No.
Okay. So very good, guys. Don't forget, you are expected to finish this discussion board by today. But remember, I'm being very flexible because I know not everyone is here. I'm missing a couple of students. So I will post the video on Schoology for you to rewatch in case you missed something. And please, if you have friends that aren't here today, tell them to watch my video. But please, please, please submit your discussion board today so we can finish all this DNA stuff. Sound like a plan?
Okay. Yeah.
Okay. I already graded all your DNA models, and I sent you guys feedback, so please look at it. If you have any questions for me, please reach out to me. Other than that, have yourselves a beautiful, safe weekend, and take care, okay?
All
right, guys. Peace. Bye, guys.
Bye.
Well,